Welcome viewer in this lecture on fundamental rotational matrix. Before this we have discussed the rotation of rigid bodies and introduced the rotation matrix, and in this lecture we will continue after that. So if we consider any rigid body with the attached fixed frame and another rigid body with attached body fixed frame, we can see that this body fixed frame is attached to this rigid body, and this rigid body is rotated by angle theta. In this particular case it is rotated by 90 degree, but we can take this theta a general rotation about z axis. This vector A can be represented or can be expressed in body fixed frame as well as in fixed frame by a simple vector with three components. Now this AB can be represented by this, which is equal to AX component of this vector A in body fixed frame, and we, by the definition of dot product, we know that the dot product of any two vector is nothing but it is the product of one magnitude of one vector with the component of that vector along the second vector. So that is why this A dot B will give us AXB, A dot JB will give us AYB, A dot KB will give us AZB. And in general form, we can write this matrix as the dot product 3 by 3 dot product expressions like this, where A in this case is expressed in fixed frame, and we get the component of vector A in body fixed frame. So we can represent this 3 by 3 matrix by letter R representing rotational matrix, subscript F is fixed frame, and subscript B is with respect to body fixed frame, or we are mapping fixed frame into body fixed frame, or we are converting the component of vector A from fixed frame to body fixed frame. So these are the different ways we can uh, call, or we can express this rotation matrix. What does it mean? It is basically converting component of vector A expressed in fixed frame into body fixed frame. If we want to use the inverse of this, if we want to convert body fixed frame a component of vector in body fixed frame into component vector in fixed frame, we have to take inverse of this. Likewise, we can also express this vector A in fixed frame, and those component of that vector in fixed frame can be obtained by taking the dot product. We will be using the basic concept of dot product. Similarly, we can write down the 3 by 3 matrix of the with expressions of dot product to convert the component of vector in body fixed frame into component of vector in fixed frame. So if we see the two equations, equation number 1 and 2, we realize that this matrix and this matrix both are transposed to each other. So we can write down that this matrix RFB is equal to RFB transpose. That is what we have written here. It means these are orthogonal to each other. That is another definition of the matrix orthogonality. And equation 4 and 3 gives us that this is equal to inverse as well. So a rotation matrix, transpose of rotation matrix is equal to the inverse of rotation matrix. So this property will be using for further analysis of robotic manipulator. Now let us discuss fundamental rotation. Fundamental rotations are rotations around about x-axis, y-axis or z-axis separately. And in this particular case, if we take this fundamental rotation about x-axis, we can use this equation for all type of rotation. Simply you have to see this is I dot IF, means we are taking the dot product of IF and IB. So it is 0. So angle is 0. So that is why it is 1. JB dot jf. For this particular case, this is jb and this is jf, so angle is theta, so that is why no, sorry, this jf, this is jf and this is if. So jf and if has 90-degree angle, so it is 0, and similarly this is also 0. We let us take this, it is jb dot jf, so jb dot jf angle is theta degree, so that is why it is cos theta. And kb dot jf, so kb is here, that this is kb, and jf is this. So angle between jf and kf is 90-degree, and then it is further rotated in this plane only, that is yz plane, then it is 90 plus theta, so that is why it is minus sine theta, and so on. So similarly we can write down the rotational matrix by using this general matrix in dot product form to get the rotational matrix of all three fundamental rotations. And when we see this, these fundamental rotations are always represented by r x theta, r y theta, r z theta. It means that this is the rotation about x axis, y axis and z axis by some angle theta. And we can in general represent this rk theta, rk, where k is 1 is to 3, representing x y z axis respectively, and so we can represent either like this or like this. So any representation we can use. We can also see from this matrix, this matrix, this matrix and this matrix, that kth row and kth column of rk theta matrix is same as kth row and kth column of identity matrix. It means if k is 1, we are talking about the rotation about x-axis, so this row and column will be there here, this row and this column. When we take k2, then the second row and second column will be present here, second row and second column. When we take t, k is equal to 3, it is third column and third row, third column and third row. Next we focus on the submatrix. After removing this identity matrix, then we see that the diagonal terms are cos theta and off diagonal terms are sin theta, but with some sign negative or positive depending on their orientation, which axis we are talking about. So to remember this, this is minus k, minus 1 raised to power k sin theta will be off diagonal term which is above this diagonal. So if k is 1, then minus k raised to power 1 is minus 1, so that is why it is minus sin theta, and the other is opposite to this. Here it is minus 1 square, so it is plus 1, and the other term is negative to this. So that is how basically we can remember these rotation matrices. The properties of rotational matrices, it is a special orthogonal group which form special orthogonal group where RT is equal to R inverse, and RT and R will be identity matrix, as this RT is nothing but R inverse. And the product of any two rotational matrix is also especially orthogonal, and the commutative law also holds good whether we take R1, R2, R3, R2, R1, R2, R3, but the sequence we cannot change. This we have already discussed. And if we represent these component of rotation matrix by NOA representation, then we can write down that this is are basically the component of x1 along x naught, y naught and z naught. So these are x component, y component, z component of x1. So this and this dot product of this and this is always 0, and dot product of this and this is 0, dot product of this and this is 0, so that is why it is orthogonal. And as nx, ny, nz are component of x1, so it will be always unity, because x1, x, y1, z1 they represent unit vector of moving frame, x0, y0, z0 represents unit vectors of fixed frame. So these conditions are satisfied, and we for reducing the size of the space required for writing rotation matrices, we use C to represent cos and S to represent sine. So this is how we will be representing for further analysis the rotational matrices. And these are fundamental rotational matrices because we are only considering the rotation about either x or y or z, not collectively. So this one example, let us say we have some initial frame and finally we want that our frame to move like this to have this orientation. So first transformation can be the rotation of this frame about x-axis, and this is the 180-degree rotation, that is pi degree rotation, whether negative or positive both will be correct. And then we can write down this is our 180-degree rotation about x-axis. So this is identity matrix. This is minus, this is due to minus 1 raised to power k, where k is 1, so it is negative, it is positive, and the diagonal terms are cos theta. This is how we can remember. And then we can uh, rotate this about z-axis in negative 90 negative direction. So it is minus 90 because if you cross your curl your finger x cross y, that is I cross j, it should give me k. So this particular rotation, which is not along this, it is y cross case y cross x, so that is why it is negative. You curl your finger in the direction of the rotation, the thumb will go inside, so that is why it is negative. So it is negative rotation. So this is how we can find out the rotation matrix of different fundamental transformations. You can go ahead for identifying the different element of this particular rotation matrix by using different properties of rotation matrix. So you can try these, and you can that is for your practice. So thank you very much for your patience during this lecture. Thank you.